Now, an epidemiological investigation, what does it involve? And much of this you already know, but I want to go over it. And there's classes that are spent on the spectrum of disease and the spread of disease because it's so important. So we have the inception of disease, which we call prepathogenesis, in factors that initiate the disease. We have pathogenesis, mechanism by which etiological agents produce a disease, and we have pathological progression. And the clinical response to the disease we classify as mild, moderate, or severe. So when you're thinking about disease inception, you're thinking whether somebody's at the pre-pathogenic stage or the pathogenic stage, or the pathological progression has reached a certain point that it's much more severe, and the outcome may lead to mortality. So when we talk about the sequela of disease, we talk about remission, we talk about reoccurrence, we talk about unremitting progression and death. And not every disease obviously results in death, but some can. So we know that if you think about a disease and remission, you think about cancer. Well, we talk about somebody being in remission. Lot of debate about what remission is. Is it temporary reduction in signs and symptoms, or is it or do signs and symptoms become undetectable for a while, but and it's due to the lack of sensitivity and specificity, cover those terms of our equipment and detection methods. In some diseases, they reoccur. Cancer's a good one to look at. We have other diseases like influenza that you have it once and then you're well and then you get it again. And then we have some diseases that just are going to progress to an endpoint that's going to result in death. So I hope this sort of helps you in ways to organize your thinking about disease in a systematic way. Now, all of these don't have to be included, but again, I want to talk to you about something that's so basic in epidemiology that it's often forgotten, and that is to define a case based on criteria. And what makes it difficult, if we don't define a case the same way, we don't progress in science in the treatment of a certain disease. So if we have multiple definitions of what a case is, we're really treating multiple problems and not a singular problem. Or if we don't have a case definition at all, and you'll read articles that don't have them, don't have a definition of a case, you don't know who really is being treated at all. Now here's another way in terms of the spectrum of disease. We talk about exposure. These are the stages you go through. You're exposed. You have a pathological progression. You have signs and symptoms. You may or may not have disease onset. And then you either have progression or reversal, disorder or disease, which a progression would lead to death, or a reversal of the disease where somebody may get better or actually remain the same but not get worse. So it says here the red text appears repetitive. Don't don't let that bother you. Also, not everyone with the disease dies from it. So this chart can be somewhat misleading. But what I'm wanting you to take away is that you're going to have exposure, you're going to have a pathological progression, you're going to have signs and symptoms, and you may or may not get the disease, or you may or may not display the disease, as Typhoid Mary did not display symptoms of the disease, and yet she had it and was a carrier. Okay, case versus non-case, you can see I'm really harping on this. A case is what you define it to be, but you have specific criteria. And what happened to us in about 1988, we were using criteria for AIDS, and we were classifying people according to meeting specific criteria, and then we changed the criteria. So after 1988, we couldn't use we couldn't use the data prior to 1988, because once you change the case stem or case definition, you're comparing two groups. Now, in order to have a case, you have to have a diagnosis, and so otherwise you have a very heterogeneous group of people that are sick. So it implies a dichotomous or a binary distinction: either yes, you are diseased, or no, you are not. And as a non-case, is someone who doesn't meet the case criteria. They don't fall into this particular disease category and wouldn't be people that we study. Now, I'm presenting this as a simple issue, but it's been debated often in the course of medicine and epidemiology as to what is a case. And that's what we were trying to decide with AIDS. And obviously we thought we had a definition, when in effect that definition changed and made data prior to 1988 useless. Okay, now I wanted to switch here because this is a behavioral example. This is a psychological example, rather than always focusing on physical health. So we're looking at somebody that might be maritally happy versus relatively happy versus distressed. And here's the criteria. And this is the marital adjustment scale. I have used it myself. There are 15 questions, and they categorize people pretty neatly into these one of these three categories. So you can decide whether or not people should receive help or not, or the couple can. And what's interesting about this too is oftentimes those who are maritally happy want to do things to increase their happiness, so it doesn't have to be for pathological reasons that we apply techniques. So we could look at this as primary, secondary, and tertiary prevention. So that's another way to examine these three categories. I keep trying to bring the vocabulary that we've covered back in so that you can utilize it as I am as we go along, so that you learn it and know it well, because that's application. Okay? Now, I've already mentioned this. This is problems with case definitions, but it's been written down, and I won't go over it because you can read this slide just as well as I can. And you know that case definitions do change, and that's a serious thing, and we just lose vital data because we haven't made a good definition from the outset. Now, steps of an epidemiological investigation. We always want to begin with determining the magnitude of the disease. How big is it? Now, you know right there that that brings into all your that brings together your vocabulary. When we're talking about magnitude, we're talking about distribution, determinants, and frequency. We're talking about a diagnosis. We're talking about incidence and prevalence, and I would add the word rates there for you. Um, and then, so we want to know, what is the trend? Is it different from the endemic state or the baseline state? Um, and we would want to know, um, is it an outbreak? Is it an epidemic? Is it a pandemic? So we're looking at person, place, and time variables again. Number two, we want to look at the etiology of the disease. Um, we want to make certain how this disease seems to be spread. We know that greater than 75% of the diseases, are you ready for this, are spread from animals to humans. So, or is it being spread by insects, or how are people contracting this particular disease? Number three, we want to know about the natural history of the disease. And really what this is talking about is the endemic state. Has it always been at a low level? Is it a holioendemic disease? Is it a hyperendemic disease like AIDS and other diseases that stay at a high level all the time, like heart disease? So what is the trend of this disease? Is it low, high? Does it affect kids more than adults? So all of those distribution factors are very important here as well. Now, we're going to develop a prevention program, and you remember that prevention is treatment. So whether you're talking about primary, secondary, or tertiary prevention, you're talking about some type of treatment. Well, in public health, what we're hoping for is a population-based approach. So we want to do something that's inexpensive, that has great influence across a population. And sometimes we can do something that's very minimal and only influence 5% of the population, but when you translate that into actual numbers of people that are influenced, it's a horrendous number. So I want you to keep that idea in mind as well, that a minimal effort can have great impact on huge numbers of people, and we call that a minimal intervention, or again, following Occam's razor, as parsimonious. Okay, we want to be able to evaluate new preventive measures, and what happens? Does a preventive measure work? Does it not work? How can it be improved? What are we going to add to it? How can we still keep it simple if we're going to add something to it? All the time we're thinking about money and the economics of it, because we can't use expensive methods for everyone. We've been trying to do that, and of course it's been breaking the bank. We need to look at things that we can do for the population that will prevent them from needing hospitalization or needing extensive medical treatment and care, and we can look to behavioral, sociological, and other ecological approaches that might provide information about how to address this problem. So we have to, we need an implementation system, and sometimes what we're doing is we're looking at policies or laws, and policies and laws are different. Laws are set by Congress. Policies are usually set by companies, and sometimes policies and laws overlap. But we might have a policy in our own town where we would purify the drinking water. We know that the drinking water in West Lafayette is potable, but oftentimes it is filled with a lot of metals and rust. So um, and and Snow did. He had a policy: water collection restricted to one well not contaminated. He shut off the contaminated well and water supply. So next, I'd like to focus on one of the basic core competencies by the Association of Schools of Public Health, and that's calculating basic epidemiological statistics. And this is a heady part of the course. The calculations are not complex. They involve addition, subtraction, multiplication, and division. So there's just four functions. It requires a knowledge of what goes into the formula, and that's what's most tricky is to decide on that, or most difficult. I don't think there's too many tricks about it, but I'll try and bring you along with the basic information. So we're going to focus on indices of morbidity or disease, and I'll acquaint you with the basic terms and the calculation processes and what to pay attention to, etc. Now, what we have is we have morbidity rates, which of course that's the risk of illness. We have mortality rates, and that has deaths from illness. And last, we have birth rates. And how do you think the economy and birth rates are connected, or are they connected at all? Do you have any idea about that? Well, what we notice is when we have a poor economy, birth rates go down. And when we look at the number of deaths associated with birth rates, or birth death rates, we find that is an indicator of the health and the wealth of a nation. So if you have high death rates in a nation, that usually indicates that they that their socioeconomic status is low. So those are just general rules of thumb that you might keep in mind as we move along in this particular area. Now, there's two important things that you have to know, or three important things that you have to know, and I know some of you have not had this information for a long time, and I'll try to go through it slowly, but at the same time so you can, in order that you remember it well. We're going to deal with ratios, and everything we're going to talk about is a ratio, and that word in itself offers confusion, but we'll talk about that in a minute. The problems that we are going to focus on are usually in this format, where we have a numerator, a denominator, times a constant. And the formula is incomplete if it doesn't have a constant. And many times what we will ask of you in a quiz or on a test is to write down the formula, because then it's a matter of plugging in the numbers correctly into the numerator and the denominator and multiplying by k. Now k in this instance is a constant, as I mentioned, and the constant is expressed in three ways. It can be expressed in regards to a unique population, a small group of population. It can be expressed in terms of the U.S. population or the world population. And we're going to look at three different formulas in particular. And the last one is a proportion. Now, usually what people think about a proportion, that it's a percentage. In epidemiology, doesn't see it as a percentage. It's a particular way to come up with a percentage value, but there's more involved than that, although epidemiology does use percentages. So I'll clear that up as time goes on, but I want you to remember that we don't generally talk about percentages in epidemiology. We talk about proportions. Okay? Now, K is to the power of 10. So you can have 10 to the fourth power. And let me just give you an example, because I know many of you have been away for a while. If I had 10 to the fourth power, you'd multiply 10 four times. So you'd multiply 10 by 10 by 10 by 10, which would give you 1,000. So if it's to the fifth, it would be 10,000. To the sixth, it would be 100,000. So that's the easy way to understand power, and everything is 10 to the nth power. So so these k's can change and do, but they're all to the power of 10. Morbidity. Generally, there are three units of morbidity: people who are ill, periods of illness that people experience. They can happen more than once. The duration of the illness, how long does it last? And morbidity is measured by incidence and prevalence. And incidence and prevalence are not synonyms. They don't mean the same thing. I hear them used all the time in the same sentence, or as one term being exchanged for another, which is incorrect. And incidence rates and prevalence rates do not mean the same thing as incidence and prevalence. Incidence rates and prevalence rates involve a calculation, and I'll go on with that here in just a second. Okay? Incidence alone is a count. Okay, so if I say, what is the incidence of the number of people in a group of 10 that are sick, you might count noses and come up with 7 people are sick. So you've just counted the number that are sick or ill. Now again, notice that the emphasis is on diagnosed people. So we would want to focus on how many are ill with the flu, and we're assuming that these people have been diagnosed and have the flu, but you're just counting. You're not doing any multiplication, or excuse me, you're not doing any division or multiplication as shown in the formula below. Okay, so incidence alone, if I say incidence rate, you're going to use this formula. If I say incidence, you're going to count. That's all you're going to do. You're going to count people. Okay? Now, an incidence rate says it's a ratio, and I'll talk to you more about that ratio as I mentioned, but the ratio that new cases appear in a population. So when I mean incidence, I mean a brand new case first identified. Okay, so our formula for incidence has to do with the number of new cases during a specified time period and the total population at risk. And we said that could be a unique group. We said it could be the U.S. population, or we said it could be the world population times a k to the nth. Okay, but in all cases, incidence, whether it's incidence alone or incidence rate, requires a diagnosis. Okay. Now, if it's not specified, if you just read something, and we're talking about an incidence rate here, or incidence in general, it usually means that it's annual. It's annual incidence. It can be a shorter time period, but if it's not specified again, it's annual. So, but for shorter time periods, it could be a half a year, a quarter a year, or a 2 week interval. If not specified, and this is what I'm trying to get across, assume annual incidence. A diagnosis is always required, whether a count, a ratio, or incidence is annual. It's always annual, whether a count or a ratio. It's always annual. The U.S. population equals 315 million as of 5/9/13. And we got this information from the population clock, and that is the population clock can be accessed at the URL at the bottom of the page, that there in red. So notice this because our population continues to grow. Now it will change every day that you're in this class, and you will see if you go to the population clock, which is interesting, you can see how many babies are being born after subtracting out those people who are dying. So based on the population clock, we have one birth every 7 seconds. So every time 7 seconds occurs, we have one new person adding to the total number of people that we have in this country. And this is after taking into account one death every 13 seconds, one international migrant every 44 seconds, and we have a net gain, therefore, of one person every 12 seconds. So I probably should say that every 12 seconds we have a net gain of a person. Now look at the world population. In April, it changed to 7 billion, April of this year. And this is going to continue to increase. And just like the United States population is continuing to increase. And you will see if you go to the population clock which countries have the greatest number of people, and we're third in the list. Now I want to mention something else that you're going to be hearing on the news, and you probably heard it already, is that at one time we had a replacement model, and we were having 2.1 children born, or every family that of childbearing age had 2.1 children. That means it was a replacement model, that those two children that were born would replace their parents. Now we have 1.9 children per family, so we have less than a replacement model occurring. But still, in terms of the population clock, you will see that our U.S. population is still growing in number, and so it hasn't influenced, it slowed it down, but we're still adding individuals routinely to the total of the number of Americans. Now, this is from the population clock, and you can see that we have 2.496 worldwide being born, and here's the total number of being born, and minus those that are dying. But this sort of shows you projections for the future. At 2050, um, the world population clock, which is real close to the world census, it doesn't differ very much. They're projecting that we will have um, this value here. That's the medium variant, or we will have as many as this number of people, which is the high variant, so 10 million, and or 10 billion, and this could be the low variant, which we would have 8 billion people. So there's also thought that we're going to run out of essential minerals necessary for life. So if the population continues to grow at this rate, we may be in a place that we cannot sustain ourselves with our food supply. Now I want to talk about mid-year because that's what we always talk about, mid-year, and I'll talk about its importance. Mid-year is usually the denominator is a mid-year for the population, and the mid-year is based on the census. The census is done every 10 years, and they sent you a card last time and you completed it, and then they sent you a follow-up card if you didn't complete it, and then I think there was a penalty if you didn't respond. But the census takes 3 years to do. So in 2010, it took 2009, 2010, and 2011. Okay, so it's a 3-year period. The mid-year is 2010. And if we had 5 years, if we had 2008, 2009, 2010, 2011, and 2012, we'd still have 2010 as the mid-year. So you might think of the mid-year as a median in on the interstate. The median is the middle area that separates lanes. So that's really what we mean by mid-year, and it seems to be the best estimate of the population because the system is up and running and there's far more problems or kinks in it. So I've already talked to you about these other examples, and here I was doing it for memory, but anyway, the answer is the same. Okay, prevalence. Now remember, prevalence alone is a count. So if I ask you what is the prevalence, you're going to give me a count. Now, prevalence means something in particular and is more comprehensive than the term incidence. So prevalence covers new cases, existing cases, and recurring cases. Okay? But for right now, you just need to remember that prevalence is a count. If I don't specify rate, rate is division and multiplication. Okay? So let's go on to the next term so you stay with me here. It says prevalence, and notice it's always going to say this, and I'm going to get to it yet. The ratio of the total number of individuals who have a disease during a specified period of time by the population at risk, and multiplied by K. Okay? And then it says what I just said. It covers new, existing, and recurring cases. So a recurring case is a person who has the flu, this is an example, gets over it and has the flu again. And in that case, the prevalence would be counted as 2, occurring 2 times for one individual. Okay, if not specified, assume point prevalence. if if it's not indicated otherwise, whether it's a count or a ratio. Okay? So recurring, if a disease is recurrent, you may count it in the numerator more than once. Okay? Persons must become sick and then completely well, and the disease is gone, they are cured, and then they get the disease again. So, and as I mentioned with influenza, they would have the disease, say, in the winter months, and then they would have influenza again in the spring. That person would be counted twice because they had influenza twice. In every case, we are interested in a diagnosis no matter what disease that we're dealing with. Okay? Next, with prevalence, there are four main types. There are point, period, annual, and lifetime. Prevalence then varies according to time, and I'll show you examples of it. Hopefully this will be a simple thing for you to remember. If not, you can replay it and look at the slides again. The same time periods as shown above can also apply to incidence, and I alluded to that earlier when I was talking about incidence. But for right now, you just think that that prevalence has four different types. Now remember, if it's not specified with prevalence, it is what kind of prevalence? It is point prevalence. If incidence is not specified, what kind of incidence is it? It's annual incidence. Okay, so you want to be aware of that and be certain you know the differences of the time period that goes with each one of those terms if not specified. Okay, now let's look at this. Point prevalence rate. It says the ratio of the number of people with a disease during a specified time period, similar to a snapshot or 24-hour period of the disease in time. So if I want point prevalence, let's say on July 1. That's a 24-hour period. That's a point. That's a specific point. I could want it on July 15th. That's a 24-hour period in a given point. So I could want it for any day, and that would include 24 hours. All right, so I want you to keep that in mind. And again, if it's not specified, it's always point prevalence. Okay, the denominator that we've been talking about, again, just as this is a way of review, I'm not saying anything different, is a unique population, a U.S. population, or the world population. And so this is, we think about this with the World Health Organization, and you can tell that we would be probably dealing with billions as the constant, or something less than that. Okay, so hopefully this is clear. Need to clean it up. Okay, period prevalence has to do with a given time frame that is less than a year. So period prevalence is 3, 6, or 9 months. Those are all examples, and usually we don't have 70 days or something of that nature. We usually have it in months, although it could appear in days. But generally that's not the case. And since I said period prevalence rate, we're talking about division and multiplication. So we want to know the total individuals with a disease during a specified time period, and we said it could be 3, 6, or a 9-month period. Anything short of a year. Okay? Now, an annual prevalence rate, because we know that with that's generally what prevalence excuse me. With an annual prevalence rate, we're talking about the ratio of the total number of persons with the disease at any time during a 1 year period. So we're looking at an annual period, and we're going to have a total population or study group that's at risk times the constant. Okay, all right. Let's go to lifetime prevalence. Lifetime prevalence, this just means whether or not you have had a particular disease at some point in your life. Not how many times you've had it, but if somebody said the mumps, how many times have you had the mumps? You'd probably say once. If somebody said, how many times have you had influenza? Even though you might have had influenza 10 times, you're going to say, yes, I've had influenza. They don't want to know the number of times. They just want to know whether or not you have had the disease. So it's a dichotomous variable. Yes, I've had influenza, or I have not. And we're looking at the population or the study group at risk times the k to the nth power. Now, this is sort of a tricky concept, and I could show it to you graphically, and it would probably be less tricky, but let me see if I can relate it to you verbally. When we mean a lifetime, this formula was first developed in the 60s. And in the 1950s and 1960s, a lifetime was considered 65 years. A lifetime is considered substantially longer than that now. We look at the late 70s and early 80s as a lifetime. So this is good for people who are less 65 and less. Now we could change in the formula what is considered to be a lifetime and take people into account who are older than 65 years of age. Recurrence is not taken into account. We only count whether the person has ever had a disease once in his or her lifetime. That's one time. Okay? So, and actually, let me correct that about lifetime, what it was considered. Actually, from 1939 to 1961, 65 years was considered a lifetime. So we didn't make a lot of improvements in longevity or how long a person lived until after that. Okay, prevalence summary. Okay, now prevalence is a more comprehensive term. It reflects the number of new, existing, and recurring cases in a population. Okay, prevalence includes incidence because incidence means new. Okay, so it's more comprehensive. Prevalence alone is a count. Okay, you learned that. Prevalence rates vary by time and have a special notation. So we will learn more about this. This is 7 cases per 100,000 people or population, and that's how you say it. Okay, 7 cases per 100,000 people. And K, which this is, the 100,000, is the reference group that usually makes the numerator a whole integer. Okay, so you notice that we have 7 here, and that was determined by looking at the raw data, and that makes this a whole integer because epidemiology deals with people, so we want to deal with whole people. We don't want 7.2 per 100,000 because generally we don't have 7.2 people running around. We have 7 people or 8 people or 6 people, but we don't have fractions of people running around. You've never seen fractions of people. Now you may think that some of your friends are fractionated and don't demonstrate the full capability of their intellectual quotient, but we try to deal with whole numbers. Now, when we go to federal tables, I can tell you we deal in hundreds, but generally, if we can, we'd like to deal in whole numbers. Okay, and I'll talk to you about K because K is complicated and not necessarily easy to figure out, but you'll get it, and I'll do my best to explain it clearly. Okay, now what we want to do is we want to be able to communicate to both the public and professional audiences. If we calculate statistics, we want to be able to convey these statistics to the public so they know the degree of threat that a given behavior is or a given disease is. And so we want to be able to communicate clearly, and usually we take into account a reference group. Okay? Now, let me try to put this into context. Which K should you use? Okay? And I'm going to sound like an attorney here, but these are guidelines, they are not rules, and oftentimes people want to use them as rules, and you can't use them as rules. You got to put your mind, you got to connect your mind to the problem that you're dealing with. So K depends on whether studying a unique group, the US population, or the world population. Okay? Study group results or general population audience, K is determined by the population size. For example, 4 per thousand is easier to understand than 0.4 per 100. Okay, now remember, these numbers, these Ks are hypothetical groups. These are hypothetical groups of 1,000 or a hypothetical group of 100. The reason why this 1,000 is preferred is because we can change this from 0.4 of a person. Because remember, we want to deal in whole integers if possible. Now, in talking to an audience, it's easier. Now, this is where it becomes trickier. It's easier for them to imagine 100 people, because you can think of a classroom and 100 people in a classroom, than it is to think about 1,000 people. Okay? They've got to stretch their imaginations, and they've got to think about 1,000 people, and often I ask them to imagine a small town or something of that nature, so they know how serious this particular disease is. And but it's a hypothetical reference group. Now notice this next statement. It sounds like it's contradictory to the one I just told you. It says, use the smallest reference group that will enhance public understanding. K are hypothetical reference groups. Well, this would probably enhance greater understanding, but in epidemiology they wouldn't like it because it's a 0.4, and that's why we use 4 per 1,000 rather than 0.4 per 100. Okay? I hope that's clear. Professional and scientific audiences generally use the standard statistical values established by the U.S. Bureau of Statistics. Use a K appropriate for a study group, U.S. or world population. There are standard statistics that I will want to teach you and that you must know, because usually we aren't dealing with special populations. We're dealing with the U.S. population, and these K's or constants to the nth power have all been agreed upon and go with certain statistics. Okay? Next. Now notice if I'm going to ask you for a general category of the three kinds of statistics that we're going to learn, rates, ratios, and proportions, all of them are ratios. What makes it confusing is a ratio is used twice. Well, you say, I don't get this. You have ratio up here, and then you have a ratio here. Well, a ratio just means one number divided by another. And all of these are one number divided by another. And it just happens to be that a rate falls into that category. A ratio means something specific because it'll have a K behind it, where a ratio, one number divided by another, will not, and proportions will have a percent. But all of these will have a numerator and a denominator. So the general category of all of these, if you were going to put Roman numeral 1 here, is ratio. And what follows under a ratio is A, rates, B, ratios, and C, proportions. And the most frequently used are rates. The ones that are preferred are ratios and proportions, and I'll explain why it's more difficult, if not impossible, to compute these. Now, categories of measurement. Epidemiology uses three types. See, I've spelled it out again because I wanted to make certain that you got it. And all three of these are called ratios. So you now know that. Okay? And ratios and proportions are all subsets of ratios because they have a numerator and a denominator, just as I've explained before, hence are a ratio, and they have a constant. Okay? So hopefully you won't be confused and you will understand. Every problem that you will read will talk about we want to complete a ratio, and people jump to the fact that it's B that they're being asked to compute. No, ratio is just a general category, and yes, you may be asked to complete a ratio, but it's going to have a numerator, a denominator, times K to the nth power. Okay. Now, distinguishing formulas. Focus on the denominators. Okay? I want to talk about these three, and I want to talk about the key operative term. Everything that's in parentheses is a key operative term. This is the best way to learn what each of these terms mean, and they are not synonymous either. Okay? In terms of a rate, we indicate that the numerator and the denominator are related. So the denominator contains all people at risk that are in the numerator. So again, the numerator is related to the denominator. In the case of a ratio, the numerator and the denominator are separate and distinct. That means you can either fall into the numerator or you can fall into the denominator, but you can't fall into both. Okay, it's dichotomous. So a good example would be gender. You're either male or female. We could argue that from a biological point of view, but I don't want to get into that. But generally, we're saying that if you're a male, you fit into one category, and if you're a female, you fit into another. And in that case, the denominator and numerator are separate and distinct. Now let me talk about a proportion. Now, what you're going to know with a proportion in the numerator, what you have there is the first value that's repeated in the denominator. Okay? And it says the denominator contains people from the numerator and remaining members of the population. Proportions do not require time. Okay. A rate always requires time, but I'll make that differentiation here too as we go along. So hopefully you understand that you want to learn the key operative terms: related, separated and distinct, and repeated, and know what those terms mean and know them well. Okay? Next, rates. Okay? Now the overarching term, the categorical term, is ratios, right? And this is a rate. And a rate has special nomenclature. It has an X and a Y. Okay, so you don't want to put an A and a B here. So with a rate, you have an X and you have Y, and you have the constant to the nth power. Okay, that's what we mean by a rate, or rates. Okay? Next, we know that the numerator is related to the denominator. In other words, some of the cases in the numerator are also in the denominator. We don't know who they are, but they're covered in both the numerator and the denominator. So usually rates are called crude because we can't separate out who's in the numerator from who's in the denominator, and we use both to make the calculation. Okay. In a population at risk, a rate measures the occurrence of an event with respect to time. So time is another dimension with a rate, and it may help you to distinguish whether you should apply a rate, a ratio, or proportion. Now, we always know that the denominator is the study group, the U.S. or the world population at risk. Now, ratios is, you notice the difference in nomenclature. We have an A and a B times K to the nth. And the numerator and the denominator of a ratio are separate and distinct. We've talked about men and women as an example, or we could talk about cows and pigs. The ratio expresses a relationship between a numerator and a denominator. The items in A are not counted or found in B. I'd just like to do a quick synopsis here before we begin. We were talking about ratios, and under ratios we were talking about rates, ratios, and proportions. And I'd like to move on to proportions. And I made a statement earlier that primarily epidemiologists don't refer to percentages, they refer to proportions. And the key operative term associated with the proportion has to do with repeated. Whatever is in the numerator is repeated and should come first in the denominator. And just to help you understand this formula a little better, why they do it this way is because you could have A plus B plus C plus D plus E, etc., to make up the denominator, and they want you to be aware of what values should appear in that denominator, and then it's multiplied by 100%. You'll notice in the rate and the ratio, they're 10 to the nth power. They are not a percentage. They're going to use and refer to a hypothetical group, and I will show you the values based on the U.S. Bureau of Statistics. That I will show you the constants in the U.S. Bureau of Statistics formulas that correspond to each one of the formulas that you will be learning, and there are several of them. Okay. Examples differentiating rates, ratios, and proportions. Example 1. Now let's pretend we have 59 people, 5 of which are smokers. Now, I think these attack skills are very important, and I think people have trouble if they don't follow them precisely. And I know they seem a little simplistic perhaps, but if you have a certain style and approach, you do much better. So for me, if I was reading the problem, I would write down the formula, I would insert the numbers into the formula, I would compute the calculations, and I would draw conclusions. That way you've got a complete circle, and you need to be able to communicate whatever it is that's necessary to the audience you're trying to reach. Okay, example 1. What is the rate of smokers? What is the proportion of the students who smoke? And what is the ratio of smokers to non-smokers? And I'll try and go over each one of these so you are clear about it. Now, when we mean rate, we mean related, right? So we know that whatever is going to be in the denominator is going to be in the numerator, and we can't differentiate those cases. When we look at the ratio, we're talking about separate and distinct. When we're talking about proportion, we're talking about repeated. Whatever is in the numerator is going to be repeated in the denominator along with several other values. And the first two are going to be the K's are going to be reported 10 to the nth power, and the third one we're going to have a percentage. Okay, information. Here we go. Smokers in a unique study group. So we're dealing with something that is more unusual, all right, because we're just looking at a small group, and we're not looking at U.S. population statistics, and we're not looking at world statistics. We're looking at a unique study group, and this is something that you might do under any number of occasions. So we'll start here, and then I'll expand your thinking as we go. So we have 59 people in the population. We have 5 people of those 59 who smoke. Okay, so those 5 smokers are embedded in those 59 people. So this is a rate. The numerator is related to the denominator, or the denominator is related to the numerator. And you notice the nomenclature. It's x divided by y times k to the nth power. So what we have is we have 5 divided by 59 times 100, because we're using 100 because that's easy to communicate to an audience, and we're going to leave it as 8.5. And I know I talked about fraction, you don't want to fractionate, but this is probably the simplest way to communicate the information. Otherwise, if we went to 1,000, it would be 85 per 1,000, and that just seems too big, too cumbersome for the size of the group. So 8.5 per 100 people smoke. 8.5 people per 100 hypothetical reference group people smoke. So that's what we would be saying. 8.5 per 100 people smoke. And that gives us a rate. Okay? And so we said they were related. The numerator and the denominator were related. So, and I've said it, spelled it out here for you again so you can see it and you get used to being able to communicate and talk this kind of language, because you're going to find these statistics reported in all kinds of papers. I have students who are employed based on these notes alone, and I've mentioned that to you before, because they know what the information means, how to report it. If they're dealing with a small group in an organization, they want to be able to talk to that group in a way that makes that group understand. Now, if I was going to be at ease with this group and they knew that I knew what I was talking about, I might say 10 per 100. So if you had 1 out of 10 people, we know 1 out of 10 smoke who come to our institution. That'd be another way to say it. But this is the correct way to say it, and you can be more liberal as you become more comfortable with epidemiology and what I'm teaching you. Okay, a ratio who smoke. Now, one thing we know about a ratio right off is that by definition, they are the numerator and the denominator are different and distinct. Okay, so you can't be a smoker and a non-smoker. You're one or the other. You're a smoker or a non-smoker. And notice the difference in the formula. We switch from x and y to a and b times k to the nth power. Okay? So in this particular case, we leave the values separate, right? So we have 5 over 54 times 100. We're leaving it the same. So the ratio of smokers to non-smokers is 9.2 smokers per 100 individuals. And so this gives us pretty good clarity about smokers in relationship to non-smokers. So 9.2 smokers per 100 individuals. Okay? Last, proportion. Now we have the same information, and the proportion says, if we look at, we have an A, so we know that whatever is in the numerator is going to be in the denominator plus something additional times 100%. Okay, so we know we have 5 smokers, right? So we know 5 is going to go here, 5 is going to go here, and what's going to be here should be 54, because that was the total of the total of the population of 59, right? So 5, notice it's repeated, plus the 54, we fractionate the denominator, we multiply it by 100%, so our answer in this case is 8.47%. Now, any of these answers would be correct to communicate to an audience. Okay, these are just various ways that I'm showing you. Now, ultimately, there's more rules as to which one you use under which circumstances and what question you are answering. So I think that's the basic point that I want to point out here. Now, there's these kinds of statistics are about the proportion who smoke in our society are found in Healthy People 2020, in the Michigan study Back to the Future, and in a number of government documents that contain secondary data. In other words, it's not primary data collected by an investigator at a university who's doing a study. It's collected by somebody else, by the government. In 2009, Indiana was second, followed by West Virginia in terms of the number of people who smoke. So we've always had a high smoking rate in Indiana. So people say that we aren't first, but we're often first in a lot of the deleterious behaviors that make people ill and often lead to mortality. Now I want to give you another example. I want to put it into words. I want to break this down for you. It says, consider the following statement. The prevalence rate of tuberculosis in the United States for 1 year period was 700 per 100,000 population. Why is this a rate? And simply because it says it is? No. Don't be fooled. We have people, you're going to find out later on, that by tradition we have people that really didn't understand the definitions of a rate, ratio, and a proportion, and so they called them by the wrong name, and they've stuck over time. But and we still use the wrong name. We still provide the wrong name about them. Okay, the numerator is cases of TB. Is that right? And it is correct. The numerator is cases of TB. The numerator is a subset of the population at risk. That's correct, because we can't differentiate. We know that if we had the original figures, that these 700 are also included in the numerator. In the denominator. So you can't distinguish them. They're the same cases used twice. Now, K is per 100,000. Is this correct? Yes, it is. Normally it is with the rate. And it indicated and specified time of 1 year. That's correct. And that's all the characteristics of a rate. But the primary thing that you have to remember is the denominator and numerator are related. Okay, let's go on to another example. What proportion of TB cases in 2008 were foreign-born people? Okay. Now, first off, we have to remember that all of the people in the pie chart have TB. Everybody has TB. Okay? And so we want to know what proportion of the TB cases in 2008 were foreign-born people. Okay, so foreign-born has to do with the yellow, right? Is that correct? The cases designated in red, we don't know whether they are foreign-born or not, or domestically born, but they do have TB, right? So we don't know what country they're from. Are you with me? So how are we going to figure this? What are we going to do? Okay, and here's you need a proportion, yes. Numerator is subset of the denominator, yes. Denominator is the whole, yes. And here we go. So what we did, because we knew if we go back and look at the original pie chart, which you can see that 5,666 were foreign-born. That's the first value repeated in the denominator, plus the additional ones who were U.S. born, plus the unknowns. And this makes up the total for the denominator. So when we get ready to do our math, we divide the 2 times 100, or 24.12% are foreign-born, okay, and have TB. Okay, does that make sense to you? All right, let's go on to the next one. How many foreign-born TB cases are there compared to U.S.-born cases in 2008? Okay, you need a ratio. Why? Because they're separate and distinct. They can't be born in a foreign country and the United States. The numerator is foreign-born. The denominator is separate and distinct, and it is U.S.-born. So this is the type of division that we would come to, and then we would want it per 1,000 cases. Okay, so all we're doing is we're dividing the 5,666 by 17,391. That gives us the numerator 326 by the number of cases, and we selected a K that we thought would be appropriate and easy to communicate, right? So we have 326 foreign-born cases per 1,000 U.S.-born cases. Rate cannot be calculated. Recall the formula. The rate is x, y times k. Related, the denominator is the population at risk, or a specific study group, and we'll get to why we can't calculate it. A rate measures the occurrence of an event with respect to time. We don't have information for the population at risk or the total population for the U.S. So if we were looking at the total population for the U.S., we'd have a rate of let's see, how many people did we have now? We had, if we were looking at the number, hang on, I'll get to it. If we're looking at the number, let me go all the way back to the chart. If we were looking at U.S. born, 17,391, we would have to divide that by the total population, which would be 315 million plus. So that information isn't given to us in the problem, although we could get it very quickly through the population clock or other government resources. Remember, this is a unique study. We might assume that these are Purdue students. Then we use the total population of the number of students at Purdue in the denominator, the total number of freshmen to seniors, which I don't know, is roughly about 40,000. So in that case, the denominator would be 40,000, depending on we were focusing on the campus and a unique population, and if we were focusing on the U.S. population, the denominator would be 315 plus million. Okay. Let's try and look at this another way, and you can see whether you can come up with the answers just by looking at it. The comparison of one population subgroup to another subgroup in the same population. For example, 95 males per 100 males in the U.S. in 2010. Well, your answer, before we get to it, we know that you're either male or a female. In that case, what you're dealing with is a ratio, okay? Because they're separate and distinct. Separate and distinct. So that's what we have, and that's how we determine that, and by looking at that example. Okay, and why? Traditionally, males are not a subset of females. The two groups are separate and distinct. They're not the same. We have a ratio. And notice the nomenclature. It's not an x and a y, but an a and a b times the constant to the nth power. Okay? Now, I always avoid this because my students in biology tell me that there are variants in sexuality, and I don't want to get into that kind of issue. And sex is a social, political, religious, legal, constitutional issue, as you well know. Well, this is just for example purposes and to help you learn the basic principles about ratios, which includes ratios and proportions. Okay. The frequency of live births in a population during a specified time period. 15.5 live births per 1,000 population in the U.S. in 2000. Okay, now think about this. This is the frequency of live births in a population during a specified time period, and it's given to, we have a constant that is 10 to the nth. We have live births, so we can assume based on the definition that this is a rate. If you might think of it as you might think of it as portion, but it's not by the way that it's stated. Another problem will help make that clarification. Notice the word frequency having to do with magnitude. Frequency comes from the definition of epidemiology introduced at the beginning of the course. Okay? Next. Why? Numerator, live births is outcome of interest. Denominator, population at large or unique groups study population at risk. Time is involved, year is 2000. Information is based on time and is used to make population comparisons. And N and D, the numerator and the denominator, are related, and these are the reason it's a rate. So if you're having trouble, review this, go back to the definitions and the problems that you will have as that accompany the manual. The relation of a population subgroup to the entire population. That is, a population subgroup divided by the entire population. For example, 60% of the total U.S. population age 15 and over were currently married in 2000. Okay? Now what is this and why? Okay, first off, we've got some indicators when we read it. It says 60% of the total U.S. population age 15 and over were currently married in 2000. So in this case, we're dealing with a proportion, and in the numerator we would have 60% 15 and over currently married. Now this is a trick. What goes in the denominator? We have 60% 15 and over currently married, right? And then we have plus singles, which would be 40% of the denominator, which were never married, separated, and that would be separated, divorced, widowed, and as I mentioned, never married. So never married, separated, divorced, and widowed would make up the 40%. So that would give you, you would account for 100% in the denominator. Okay, why? Numerator is a subset of the denominator. N, age 15 and over, and married. We're going to repeat it again. all U.S. people age 15 and over who are married and are unmarried, which includes single, separated, divorced, widowed, and never married. Okay? I guess that would be single, so don't let that confuse you. Okay? Answer is a proportion. Okay? The value in the numerator is reported first in the denominator, and this is going to be reported as a percentage. The other two examples, they would be reported they would report it as power to the nth degree. Okay, additional information about rates. You should convert awkward fractions and decimals into whole numbers if you can. Sometimes you can't. It's just not possible. So, but if you can, they're easier to communicate because epidemiology deals with individuals and whole individuals. Okay, it doesn't deal with fractions of individuals. Now, I don't mean paraplegics and all this other kind of stuff. People ask me about that all the time. I says that's a whole person. For epidemiology, they count as an individual. Next, rates, ratios, importance, and proportions are all classified as ratios, right? We learned this in the beginning because one number is divided by another number and multiplied by a k, which may vary depending on the numerator and what is easiest to communicate in the type of formula. So we know for a proportion it's 100%. How to express rates and ratios. This is difficult because it depends on the situation that you're dealing with. So I have guidelines here, they're not rules. Rates often presented as follows: per a power of 10. We know that about them. Rare diseases are often reported per million because otherwise we'd have a huge fraction. It might be 0.00, it might be 0.0004 or something, and if you didn't multiply it by a million, you'd have a fraction that would be impossible, and you wouldn't be anywhere near a whole and complete person. And so those are, just a couple of things that you ought to take into account.